Discuss about the concept of Lorentz force in this video. If you like this concept, you please subscribe and share to others, and you also press the bell icon so that whenever we post a new video, it will come to your notice quickly. Okay, Lorentz force. See, up to here we have studied magnetic force acts on a moving charged particle. In this concept, we are going to throw a charged particle in both electric and magnetic fields simultaneously. This charged particle is going to subjected with both electric and magnetic fields. See, when we apply electric field, external electric field, when we apply external magnetic field, if a charged particle is thrown into this, then a charged particle is in motion, it produces electric field as well as magnetic field. So electric field of this charge interacts with the electric field. Magnetic field produced by this charge is going to interact with the magnetic field. So we know electric force is Q into E bar. Electric force is QE. Magnetic force, vector notation, force experienced by this charge can be written as Q into V bar cross B bar. So Lorentz force is the vector sum of these two, that is Fe bar plus Fem bar. First case, for example, if I apply electric field along the x-axis, magnetic field also along the x-axis, electric field vector E bar can be written as magnitude of E naught into I cap. Magnetic field vector is also B naught into I cap. Now what I am doing, I am throwing a charged particle, positively charged particle, in the direction of both electric and magnetic fields, for example. That means even velocity vector is V naught into I cap. Okay, now see carefully. This charged particle is in motion, so this charged particle can produce electric field as well as magnetic field. How much amount of electric field does this charge produce? How much magnetic field does this charge is producing is immaterial. Even we are not trying to calculate these values. But this charge can produce electric field and this charge can produce magnetic field, that we know. A magnetic field interacts with this magnetic field. So we know magnetic force, formula in magnitude wise is QVB sin theta. QVB sin theta. So interaction of these two magnetic fields produces force. That force we are calculating. That force Fm is equal to charge of the charged particle is Q, velocity of the charged particle is V, applied magnetic field we should take, we are not bothered about this magnetic field. This magnetic field is not there in this formula, remember. B is applied magnetic field, so that applied magnetic field, then theta is the angle between magnetic field and velocity. Magnetic field and velocity. In this case, it is 0, so sin 0. So that's why magnetic force will get 0. When there is no magnetic force here, there is no acceleration here. That means V remains constant. V is equal to constant. V is constant. So V is constant, then the charged particle follows a straight line path. Okay, this is all about magnetic force. Similarly, I would like to calculate electric force. This field and this field are interacting electric field force is QE, we know from the first lesson. So electric force FE is equal to charge of the charged particle is Q, applied electric field is E. C, the electrostatic force will act on the charged particle irrespective of its projection. In whatever the way you project, doesn't matter, electric force will act. But magnetic force, in two cases it will not experience force. When we throw in the direction of magnetic field, when we throw opposite to the direction of magnetic field, magnetic force is zero. In all other cases, magnetic force will act, but magnetic force only changes the direction of the charged particle without change in the speed of the charged particle. Okay, so in this case, electrostatic force is acting. So electric force is acting along this direction. Force along this direction is F is equal to QE. So acceleration also will be there in this direction. That acceleration, force can be written as MA into QE. So acceleration is QE by M. QE by M. So along this direction, acceleration is QE by M. So this acceleration can increase the speed of this charged particle. But magnetic force is zero, magnetic acceleration is zero. Magnetic force is not going to increase the speed of the charged particle. But whereas electric acceleration is going to increase the speed of the particle. So the charged particle moves along the straight line with increase in velocity because of electric effect. So now we are going to write the Lorentz vector, Lorentz force F bar is equal to magnetic force bar plus electrostatic force bar. Lorentz force becomes, this is zero, we have only electric field force. So now the Lorentz force F bar becomes, Fe value is QE, but it is in the direction of positive x-axis, so that's why we can write like this. In this situation, this charged particle is moving along the x-axis with increase in velocity. This is case 1. Now we will see second case. In second case, we have applied electric field along the x-axis, magnetic field also along the x-axis, whereas the charged particle, positive charge, is thrown along the y-axis. Velocity is perpendicular to both magnetic field and electric field. See in this case, first I'll study about magnetic force. So magnetic force Fm is equal to QVB sin theta. See here, magnetic force will act on this charged particle because angle is neither 0 nor 180. In these two cases only magnetic force is 0. But now here we are projected with an angle theta is equal to 90 degrees. So magnetic force, charge is Q, velocity of the charged particle is V, applied magnetic field sin 90 degrees. Sin 90 is 1. So magnetic force is maximum, QVB, force is maximum force. Okay, see here, force is a vector physical quantity. It will have magnitude and direction. Magnitude we have represented here QVB, but we should know its direction. The direction of magnetic force acting on a charged particle can be known by using Fleming's left hand rule. Here we are going to apply Fleming's left hand rule to know its direction. See here, FBI, Foreign Bureau of Investigation, FBI, easy to remember. Magnetic field direction represents forefinger. I have opened only magnetic field. Okay, now I should know current direction. Current for a positive charge, current will be in the direction of motion of the charge. So current will be in this direction. So these two fingers are aligned. So you can open thumb. Then magnetic force acts into the plane of the board. So that means this charged particle is imagined here. Magnetic field is in this direction. Velocity is in this direction. Force acts in this direction. So this charged particle revolves a circular path like this. It revolves a circular path here. Okay. Because of the magnetic force, charged particle moves in a circular path. It's a circular path. Radius we know, mv by qb. Okay. Its time period we know, that is 2 pi m by qb. Everything we know. As long as this velocity remains the same, the radius will be remains the same. If this velocity increases, radius also increases. This already we know from our basics. So this magnetic field exerts force on this charged particle, because a moving charged particle produces magnetic field as well as electric field. This magnetic field and this magnetic field are interacting. So force is experienced by this charge. This is into the plane of the board. So the charged particle moves like this. This is only effect of magnetic field. We will see the effect of electric field alone. Later we will combine the magnetic effect and electric effect both. Understand this carefully. I have studied the magnetic effect on this charge, magnetic field effect. Now forget about magnetic field for some time. We will see how electric field will influence the motion of the charged particle, that we will see. See, when a charged particle is in motion, electric field will be produced, magnetic field will be produced. This electric field and this electric field will interact. That interaction exerts force. Electric force, we know that is QE. Electric force always acts in the direction of electric field for positive charge. If it is a negative charge, electric force will act opposite to the direction of electric field. So here, in this case, electric force will act in this direction. That electric force magnitude is this. Direction is this. Now, electric force is trying to take this charged particle in this direction. But velocity is there in this direction. So due to velocity, particle should go in this direction. So that's why the particle will move in a resultant direction in a parabola path. If we have alone electric field, then the path followed by the charged particle is parabola. But understand, it is very, very, very important. Due to electric field, velocity of the charged particle increases. Force is acting along the horizontal direction. So that's why acceleration will be there along the x-axis, along the horizontal direction. This acceleration is QE by m. Okay. Here, initially, there is no initial velocity along the x-axis 0, but there is a velocity along the vertical component, that is uy is v, but force is acting along the x-axis, so acceleration will be there along the x-axis. Acceleration along the x-axis is QE by m. So final velocity along the x-axis increases. It is 0 now, it becomes 1, 2, 3, so on, it increases, Vx increases. But acceleration along the y-axis is 0. So when there is no acceleration, velocity is constant. Vy value is again v. Vy value is v. That means this component is not increasing. Whereas this component initially 0, but as time goes, velocity increases. This you have to remember carefully. Okay, so effect of only electric field will be a parabola. But now what I am doing, understand this one very carefully. Now I am going to study the combined effect. We are going to study combined effect. See, electric acceleration is along the x-axis. Magnetic acceleration is qvb by m. This will act towards the center, this side. Acceleration due to magnetic force, magnetic acceleration, magnetic force is into the board, magnetic acceleration also into the board. But magnetic force, magnetic accelerations are centripetal. They never increase the speed. Only they involved in changing the direction. So this is very, very important. So there is no acceleration along the y component. There is no acceleration along the y component. So y component remains the same. But x component is keep on increases because of the acceleration due to electric field. This is clear, no? So now what we are doing, see carefully. This component tries to make the charged particle in a circular path. Circular path of radius r is equal to mv by qb. This velocity remains the same because there is no acceleration along this component. So radius of the circular path remains the same. Okay, but we are going to get horizontal component of velocity. Horizontal component of velocity. This horizontal component pulling the charged particle in this direction. So that's why when you take the combined effect of electric field and magnetic field, the charged particle due to magnetic field it is in circular path, due to electric field it is going like this. That means this charged particle is going to have helical path. Helical path. Remember here, when the charged particle is moving in a helical path, we have calculated pitch of the helix. Pitch of the helix. Pitch of the helix is horizontal component of velocity into time period. Okay, na? See here, horizontal component of velocity is increasing, but time period constant. But horizontal component is increasing, so pitch of the helix increases. That means here charged particle moves in a helical path, but the radius of the helix remains the same. Radius of the helix remains the same because this component of velocity remains the same. Whereas horizontal component of velocity is increasing, so pitch of the helix increases. Pitch of the helix. Pitch of this helix is here, this one, x. Now next pitch will increase. Next pitch increases. Next pitch further increases. Next pitch further increases. Next pitch further increases. So like this, this charged particle is moving in a helical path, but radius of the helix remains the same, but pitch of the helix goes on increases. This is very, very, very important. Now in this case, how to write a Lorentz force? Means Lorentz force F bar is equal to magnetic force is QVB magnitude, but direction is into the board. Into the board can be written as minus K cap. This is magnetic force plus electric force. Electric force is simply QE, but that force is acting along the x-axis. That's why we can write it as I cap. So this is how we are going to represent the Lorentz force.